It's my great pleasure to introduce our own Polo Chow. Polo is an associate professor in the School of Computational Science and Engineering, and will be telling us about his work towards secure and interpretable AI. Let's welcome Polo.
Thank you. Thanks, Key, for the introduction. I believe mic is working good. Today's talk will be an overview of the work that we do in our group, and focusing on two areas: security or secure AI and interpretable AI. And that is a main theme of what my group does. And I like to name things after myself. So my group is called the Polo Club of Data Science, which combines artificial intelligence, or kind of the best from that side, and also the human intelligence, human HI, if for short, and to develop scalable interactive tools to make sense of complex data and large-scale model. And a lot of the work that I present work done by my students. So the current lineup at the bottom, so I need to thank them first, and then I'll claim all the credit afterwards. So we work with a number of areas I work in my group, and human-centered AI is one, where making sure that people understand what's all these latest development in AI and machine learning. Cybersecurity has been our main application area for a long time. And since these days, people do care about security, not only for the traditional sense, but also for machine learning. So which is why now we're also studying adversarial machine learning, which you will see some examples for, meaning attack and defense for machine learning. And we also have been working a lot on graphs, so a lot of graphs mining and also visualization, and also in the application area of social good and health. But for today, we're going to focus on two main areas: secure AI, or think of it more adversarial machine learning, more general, and then interpretable AI. So you may ask, why these topics? So why focus on them and how are they related? So they have very interesting connection. So for the secure AI side, I don't need to convince you too much. You already seen some unfortunate examples of how now AI can be used in safety critical application. If you don't do it well, then you can kill people. Right? So making sure things don't break is important. You may say, well, safety is critical. What about everyday life? So actually, everyday life now we're seeing AI security problem everywhere. So there's a cartoon there that says that, well, in the future, that we have the smart toaster that may go haywire. It turned out that we do have it now, smart toaster to exist. So you can get one right now. AI security is an increasingly big problem. So actually, there are only going to be even more problems like that. So it's great. So people are working on AI security. You would say, well, use machine learning, AI, and so on. But the current state is that for a lot of the things that we develop, especially if you say, oh, I have an attack technique, so we attack the model, or you have a defense technique to protect the machine learning AI model, most of the time we don't really know what happened. Often it's because we use the machine learning AI as a black box. And not really good. So ideally, what we want to do is to probably open it up a little bit, maybe not completely make it transparent, but at least know a little bit about what is happening, right? So that when it doesn't work, we know how to fix it. So when it breaks, we know how to fix it. So our goal is to develop these interactive, scalable, and usable techniques to help people understand large-scale, complex machine learning models. So today's agenda will cover present some of the latest work that we do in our group in the two areas, and also we'll make the connection among them as we go. So on the secure AI side, we'll give examples of some of the latest attack and defense technique, and also if you are interested in trying those out, we'll give you some examples like how you can do it. We call do-it-yourself adversarial machine learning. And then on the interpretable AI side, we'll talk about some of the latest work, for example, work that we developed with Facebook on understanding large-scale industry-scale model, and also with Google, we developed a tool to help people understand GAN. GAN is one of the latest deep learning technique. And also I want to conclude with a summary of the current research landscape. So if you're interested in working in both areas, so where we might want to go next. So we'll start with the secure AI side. And easy to understand, the goal is to study the machine learning vulnerabilities, and so that we can develop something that's more secure, right, more safe. And I'll give you some examples in two categories. One is the attack and defend technique of AI, and then also how to make it easier for you to try them, do it yourself. So we start with the first one, that shapeshifter. And often when we talk about security, we need to think about both attack and defense, and often attack is easier. In general, just being the bad guys is easier than being the good guy. So being a bad guy, you just break things once, and then that's it. The system is broken. As a good guy, you need to kind of protect against every possible kind of vulnerabilities. So shapeshifter is an attack technique. You may ask why we are studying attack techniques, because you want to have strong defenses, you need to think like the bad guys. So that's why we also want to be bad guy in a good sense. So think about how to break things. So shapeshifter is the first, we call targeted physical adversarial attack for object detection. So a lot of technical term there. What does that mean? So first, to understand what is really object detector, or why are we attacking it? So you might have seen a lot of examples already about what we call image classification. As a given an image, you give it a label. In this case, well, image of like this, then you'll probably say it was an image of a car, right? So, but then if you really zoom out a little bit, or maybe have a lot more content in your images, then you realize, well, maybe a car is not a good description for it. So there's actually a lot of things happening. So a lot of objects in it. Right? There are people there, there's some buildings, there's even more cars, so why would you label it just using a car? Right? So that's the differentiation there. If you're using object detection technique, you are trying to extract, localize what are the things in it, and for each of the things object, you label what it is. Right? So shapeshifter is to attack these kind of object detection. So that means not really attacking, turning a label into a wrong label, but now we're actually doing something to the individual object. It's turned out to be harder. And whether you're doing image classification or object detector, now we can pretty confidently say that all of these are actually pretty vulnerable, especially these days when you're using deep learning technique or deep neural network, very vulnerable. So you've probably already seen this from popular news, where the image is that's an image of a stop sign. You can change the pixels in ways that human being eyes can really see. Change a little bit darker, a few pixels darker, a few pixels lighter. Then you can make it be classified as whatever you want. So benign is stop sign, but after some changes, you can change it to whatever you want. So in this case, we can change it into a stop sign, limit sign, right? So actually it can be anything. So very, very easy. So anyone want to do it. But however, often we assume that bad guys have access to, we call everything almost. We call that white box attack, as in knowing all the details of a model, which is why you can really optimize exactly what to change, how much to change. We also call this a digital attack. But in practice, you'll see that, well, that may not be a practical threat model, as in maybe there's too many assumptions about a bad guy. So for example, as in if you say you are building a self-driving car, like a self-driving car, you want the car to recognize, is there a stop sign, is a pedestrian, and so on. So if you think about how do you build this system, is your car probably needs to capture what's happening on the road, and then you do some processing within the car's GPUs, CPUs, and then do the recognition right, and on board, and then figure out, oh, that's like a stop sign. So currently, all those a lot of research, the assumption is that they have full access to the whole system. Right, so that means the whole thing you have access, and then you can launch this digital attack to determine what thing to perturb. So in practice, we know that is quite hard. Right, we can hack into the system and then do all these, then maybe you don't really need to do the auto perturbation. You can just do other things. You can just crash the car if you want, right? So that's the current limitation of the attack work. So what we're thinking is, well, instead of making a lot of assumption, what if our attack is about manipulating the physical world, where we don't really need to hack into the car, but then we can easily, let's say, put something on a stop sign, or maybe replace it, reprint a fake one, but then we'll put it in the same place. So what would happen? Right, so that is what we call the physically realizable adversarial attack, and that is what shapeshifter is about. Right, so we think it's more realistic, and also we can launch both targeted and also untargeted attack. So before we go into the details, I want to first show you some videos of how that works. So this is an example of shapeshifter attack. On our student, Shang, maybe not here. Yeah. So he's the person who drove the car. So the video that you're going to see, so he drove the car, is on the top of a parking lot here in Georgia Tech. And you'll see here that he put the stop sign on the left, real stop sign, and the fake stop sign on the right-hand side. And then he'll drive towards the car. Sorry, the two stop sign. You'll see that the left one, the real one, consistently get recognized as the real thing. And then the fake one, you don't really get any recognition until maybe when closer, then it becomes many person, a lot of person. So this is possible, so then you can turn stop sign into person. So we'll show you a few more examples of that. So that you get an idea how that works. We're attacking object detector, localization, and so on. So actually there have been work on doing physical attack, but a lot of time they are focusing on image classifier. For example, you may have seen like putting stickers on stop sign, but that's not attacking object detector. It's you're turning the whole image label instead of doing the localization and attack localization. So we may say, well, what about if we apply these attack technique that works for image classifier? Can it fool the object detector? It turned out no. So earlier work found that no, that's not. Once you do the technique, apply the technique that worked really well for image classifier, you apply an object detector can recover that. So you see stop sign correct, person is correct. So how does our technique work, right? So specifically, we attack the object detector called faster RCNN. It's one of the state-of-the-art object detectors. And we want to give a little overview about how it works so that you know how the attack works. Right? So how it works is that it passes an image. So we have some complexity internally. And what it happens is internally, it should try to figure out what are some potential we call region proposals. That means what are the potential objects that you would detect. So actually they would try to figure out a lot of potentials there. And the main idea is to see if there's enough overlapping regions. So let's say around the stop sign, there may be a detection that we can do. And if there's enough such regions, then we say, oh, maybe we should want to, we do want to do a classification for that. Right. So you can discover a lot of potential regions, and then for the promising regions, you do the classification. So stage 1, stage 2, localization, classification. So what that means is if you want to attack this kind of faster RCNN model, you need to attack multiple regions. So here we're doing an illustration there. The rectangles are the potential regions, right? And they can be overlapping. Right. So that means if you want to turn this stop sign into, let's say, a person, you need to fool all those regions at the same time. So in some sense, it's like attacking an ensemble model. So attacking ensemble, much harder than attacking a single thing. And the second challenge of attacking faster CNN is that because you're dealing with the environment. So, right, so physical world, nature. We need to worry about distances, how far the thing is. Are we going towards the stop sign? What kind of angle are we approaching it? Even the lighting, like as in if cloud pass through the sky, it's going to mess up your attack. So in practice, yes, actually it does. So you need to handle all these cases, right? So in this case, adversary of our adversarial technique is actually nature. So we need to take care of that. Right. So what's our solution? So the first one, tackling the ensemble is instead of minimizing classification also, then we do optimization, which pixel to turn and so on. Instead of optimizing over one single region, now it's minimized across a sum of regions. So in other words, you want attack to work in attacking the combination of all the regions. And also, we specifically take advantage of the fact that, well, so we want something that maybe people will still see is normal. Normal as in, well, it still looks like a stop sign, but in practice it's not. So we only perturb the red area. So red area, so if you're studying human perception, or maybe taking visualization HCI classes, you'll know that for a darker area, you can actually do a lot more to it, and people still cannot see it that well. But since we're here, we're fooling the object detector, which is a computer program, we can actually take advantage of that and then perturb a lot more in the dark regions, while still remain less perceptible to human beings. So we can add that we call a deviation loss, so focus more on the dark region. And then what about handling the physical world, right? So to make the attack robust to the real world distortion, right? So potentially many ways. You can have different angle, different distance, different rotation. So we adapt the technique called expectation over transformation. So at the high level, what that means is you're attacking the average of all these potential things that you can do. So you attack the average, attack the ensemble, and then you combine all these, then that will give you the shapeshifter technique. So you may ask, well, so previously we saw turning stop sign into a person. What about making it invisible? So on target attack. So actually, yes, you can do that also. So you don't see it. You still don't see it. Maybe there's one. No, you don't see it. There's one frame, 2 frames that classify into bird. So of course, if you go much closer, you'll start to see that it doesn't really look like a stop sign. But from distance, you probably will say, "Oh, yeah, it is a stop sign. What are you talking about?" So pretty scary. So you do work on a security problem. Hopefully, we don't see that anytime soon. But DARPA does recognize that could be a threat. And so shapeshifter is one of the motivating factors for the new program called GARD, which is Defense for AI, and highlights shapeshifter as one of the state-of-the-art physical attacks that they do want more research on to help protect against it. Okay. So enough about attack. Right? Attack is scary. So how do we be the good guy and protect against it? Right, so that is what we also work on. So they gain experience, gain new knowledge about tech so that you can come up with better defense. So Shield is one of the defense techniques that we're working on. And our goal here is to aim for something that's fast and practical so that people can use immediately. So that was published at KDD 2018 and a joint work with Intel. So the current landscape in adversarial machine learning is there's a lot of techniques from a tech side. Often it's because it's easier to publish. So you're a graduate student, you're an advisor, you're thinking, oh, okay, well, how do we promote more papers? So paper being a bad guy, attack is easy, right? So you break it, then you're good. On the defense side, it's much less work because it's hard. You need to protect against many things, right? So as I said, being a bad guy, you only need to attack once, break it once. Being a good guy, you need to protect against everything. And among the defense techniques, that even fewer is on focusing on fast and practical. So a lot of the techniques, that's a dirty secret, is for both attack and defense side, often these techniques are very time-consuming, computation-intensive. And there's a joke that we said is, well, when you do this kind of research, you're killing a lot of trees, and which is true, because you're running on all these like tens or hundreds of GPUs for hours, for days. So our focus here for Shield is to want to have something that's fast and practical so that people can use it right away. So what's the main idea? So this is a good image to summarize that. So you may recall from the stop sign example where we say what then the bad guys do. So we can change the pixel, right, in imperceptible way, right, to our eyes. You can make it darker, make it lighter, right? So that could, you can think of as the attack and the top side, right, where you top part where you have an image of a dog. Right, you can change it to whatever you want. In this case, we change it into chainmail, right? So chainmail, you change some pixels. And if you without protection, then of course it gets misclassified. So our main idea is to say, well, if your technique claims that you're doing these imperceptible changes to images, then what about our defense is to exactly remove that, right? So you probably have already been using this defense technique that I'm going to talk about, which is essentially JPEG compression. So as you want to save image for the web, well, you want to compress it, make it smaller. Right? And how the JPEG compression works is to remove things that human beings usually cannot see. So technically, the high frequency noise. So that corresponds exactly to what the bad guys try to add, right? Because their claim is they add things that people cannot see. So we'll remove those. So that's the main idea. So how we want to apply it is no matter what kind of images, whether it's perturbed or adversarial or benign, we don't care. We just pass it into our Shield protection, and then hopefully we will correct those, and then wrong things get misclassified, correct things don't get hurt that much. But that's the main idea. So that's the middle part, the Shield part. So how does it work is that, well, JPEG compression is great, and we also leverage the different kind of compression level in compression. So you can compress it more as in lower quality JPEG, compress it less, and a high compression level. For example, here the one at the top, less compression, so you see fewer artifacts. The one at the lower part, there's more compression. So generally, you don't want to have a deterministic approach for defense, because if the bad guys know that's how it works, well, they can just protect it. So that means you want to have some kind of randomization. In practice, the more is probably the better. So we try to incorporate that idea. So that means when we have an image, let's say the orange square here, we try to split it into 8 by 8 blocks. And then for each one, we take different kind of compression level, like sometimes a higher compression level, sometimes a lower compression level. And we call this technique SLQ, stochastic local quantization. Very fancy name, but you already see how it works. So you just chop out the image, apply different compression level. Then that is only one of the techniques. So in practice, often defenses, you do need to use multiple approaches. So SLQ, what you just saw, that's one of the approaches. We also incorporate what we call model vaccination. So model vaccination here, that means we want our protection to be able to understand if there's some JPEG artifacts that are introduced by the compression, can it account for it? So we we incorporate those we call through retraining to help the model to differentiate between the artifacts and non-artifact. And also ensembles, we have more than one using one quality, so multiple qualities, and all these put together become the shield protection technique. So when you apply this on a text, so there's quite a few these days on our tech techniques. Some is called FGSM, tech techniques, and also IFGSM, and these days have PGD and so on, for those who are working on it. So how well does it work? So without protection, that is the great line at the bottom. So accuracy drop a lot. So model accuracy, lower the worse, higher the better. So no protection, very low. So once you do any kind of compression, that helps. So that's the purple line. But you see, if you only apply one compression level, it can also drop quite a lot. So if we do our shield approach, doing an ensemble, combining everything, that's the orange line, then we can still maintain a pretty relatively high. So eventually everything, once you have very strong protection, everything is going to go down. No, I guarantee you. But the question is how much can we widen the gap? Right. Oh, so we already have that. And the focus on our approach, as we mentioned, is we want something that's practical, right? Things that people can use right away. So we compare with existing potential techniques, for example, using median filter, which is also removing noise, and also total variation denoising as well. And JPEG, our approach is much faster, actually 10 times more, 20 times more faster. And so that means this is something that people can use right away. You don't need to wait for a long time. And that's also something that Intel has been very interested in incorporating in the technology stack. And you might say, well, compression seems really simple. Yes, that's by design. And because we want it to be something that maybe help with other kind of a technique, other kind of modality. So for example, for attacking speech or text-to-speech, we can also use compression too. So for example, one kind of attack would be to turn the sentence, let's say, open intel.com into, into another phrase where then, do I have to? Oh, sorry. So Intel there should be evil, open evil.com. So you can change it again, like images, into whatever you want, right? So, but we can incorporate compression also. So in this case, we have a system called Adagio, which uses the same idea, compression. Of course, for audio, it's different kind of compression. It will be MP3 and others. And Adagio was published in PKDD, also collaborated with Intel. And it have an interactive UI, so you can actually play with it if you like. You can upload your own audio example, do the transcription. You can try some of that tech technique, and then also apply the defense. And so I'm going to show you a quick video demo of how Adagio works. So here, when there's nothing, there you can start to upload your video, right? Create a card, upload your audio sample, load a WAV file, let's say, the computer, and then you can do the transcription, right, into text. And now you can do a tag, right? You can say, change the transcription. Again, you can change whatever you want. Digital attack is very easy. So, and launch attack very slow, which is why you're speeding it up 20 times. And then it can turn to whatever transcription you want, right? So turn to whatever you want. Now you can do the defense. So attack first, and then you launch the defense. Defense much faster. In this case, we can use compression, MP3, similar to JPEG, very, very fast. You can do it in real time, and then it can correct the mistake. So this is something that you can try. Very easy. And that's actually one of the examples of what we call the do-it-yourself adversarial ML. So oftentimes we have so many attack and defense techniques out there that can be overwhelming. So how do we know what works against what or what doesn't work against what? Right. So that's our main goal for making this do-it-yourself. So Adagio is one example. And more generally, we have now the ML exploit framework, which is also collaborative with Intel and open source, which specifically is designed to make it easier for people to try. Try as many as you can. So we recently presented at Black Hat Asia with this, and also as a KDD19 showcase. So at a very high level, we want to abstract or be able to for researchers to provide these, we call the research module, as in attack, defense on different modalities, as modules that you can add to the ML exploit framework, so that the user, this case could be researchers, students, could be practitioners, that can interactively try out these different techniques. Right. And also we want to build a community around it, so we allow people to continue to update, so that it's a good collection. And also we want to make it easy to use. Right. So our main hurdle often for research is that, well, we do all the great work, publish paper, and that's it. Right. But most people don't read paper, or they may not have the sufficient knowledge to read all the details, right? But then we want people to get people excited, especially for students. They're only starting and want to say, what does it do? So we want MLSY to provide that kind of experience. So currently we have a number of modules already. Some are on Shield, which you saw already, and also some technique, attack and defense technique. We also have from our other Georgia Tech researchers more on the malware side. So Linux malware, PDF malware, and also the attack and defense bypassing Android malware detection, AV-Pass, made a lot of news a year ago or so, right? So all these become modules of MLSY, which then the users can use. They go to a web browser. You can upload your example. It can be images, can be software, and so on, and to the MLSY framework. And then through the UI, you can pick what you want to try. Right? You want to try what attack techniques, different technique. You can create your own combination of experiment, and then look at the result. So a little bit of technical detail, we want to make it extensible and want people to actually use it. So our architecture is we have the research, attack, and defense module. We call that research module overall. And then we are user front end, right? Portal that people will use. And then we have the back end. And if people want to launch a more computation intensive work, they can then launch the worker instances. So a little bit more technical detail. Also, we want to make it easy to install. So one click, install current line. But we want to make it even more easy, and that's work in progress. So we want to be able to do it one click even on AWS or Azure or Google Cloud. So I'm going to show you a quick demo of how MLSY works. So this is the entry point to MLSY. It's quite tiny. The main focus here is on the right-hand side. These we call the pipeline. So pipeline, as in each little rectangle there, is actually a research module or configuration of research module that you as a user can select and choose what to do. So that means you can string together, as in Adagio, you can string together an attack technique, pick whatever you want, and then you pick whatever defense you want, right? And then you create a pipeline, you upload your data, you run your pipeline through the data, and then you see the result. So all these without programming. Right? So, and of course, you can look at all the detail. That's what the expansion of the law will give you. Right? And MLSY open source very, very recently, and also now it's being incorporated into Intel AI courses, so that we want to expand the education impact to have more people to learn about adversarial machine learning, and also be able to try that. Right, so those are a few examples of the work that we've been doing on the secure AI side. So as I mentioned, working on attack and defense is great, very exciting, but often we don't really know what's happening internally at the model when you say, we have successfully attacked this model, we've successfully defended this model. In practice, often we just look at those high-level number. You really say, wait, what's really happening, particularly our deep learning model, particular new one? Not really, no. So that's the dirty secret. So that means we do want people to know, and we should be working on how to make that easier for people to know. So that's what we bring us to the second part of the talk on the interpretable AI side. So I would say for practitioners, you don't need to convince them as much about the need for interpretability. Actually, practitioners, that's a main focus of their work. Right? Often when they deploy something, they don't only want to know that how it works in the beginning, but they want to make sure that they can maintain it. If things break, they want to know how to fix it. Right? So that means they want to know why and how all these techniques works. So how do you do that? Different approaches. One, you can use textual explanation, right? And our main approaches is to use scalable interactive visualization as a medium to connect the users who want to understand this model to the actual model. Right? You may ask, why interactive visualization? And the main reason is that can leverage what is good, powerful that human being can do. So machine learning is great at finding patterns, and while visualizing is great at amplifying human cognition. Right? So our eyes, our brains are really great. So we can spot patterns that computers have still a hard problem spotting. So by creating the interactive visualization, we allow the user and the visualization to incrementally together make sense of the model. So which is why interaction and visualization. Right? So for this part of the time, I'll give you a few examples of some of the interpretability work that we have been doing. We'll start with one that we collaborated with Facebook on developing a visualization tool that can help internally Facebook data scientists and engineers to understand industry scale model. And then for the second part, I'll give you an example called GANLab, which is to help students, practitioners, and researchers to understand how to use one of the GAN technique, which you with a lot more details. So it turned out that a lot of these models that these days get so complex, even learning about it before you use it can be difficult. So GANLab is one of the tools that help make that learning easier. And now I'll conclude with the research landscape about interpretable AI, so where we are currently and also where we are heading. So we're going to start with the first one. So Activis, that's the name of the system that we developed at Facebook. So now it's deployed, and of course it's joint work with our Facebook collaborator. And you may be surprised. So often with tech companies, you say, wow, they have all the resources, Facebook, Google, and all those. And visualization tool is still something that's sorely needed. Because internally, they're also differentiating between the people who build or engineer the machine learning and also people who use the machine learning. Right? For example, data scientists, they may be more interested not so much in the internal machine learning, but instead using those to analyze data. Right? So that means there is strong need for visualization. But then they need to deal with a number of practical challenges, especially at Facebook, is that the data and also the model often is very complex. Data size is huge, and also they need to deal with many kind of data. Right? So images, text, anything you can imagine. So Activis started, or was developed over 11 months, and it started with participatory design sessions with over 15 researchers, engineers, and data scientists at Facebook. And now Activis is deployed by Facebook, and behind it is a screenshot. We'll look at some of the component of the system and what are the challenges that is solved. The very first one is about the complexity of the model. So like many tech companies, the model that they use can be big and complex. So what that means is if they're looking at deep learning model, for example, I could have many layers, and for each layer could be many neurons. Right? So pretty overwhelming. But we observe that, well, even though there are many, many layers to the actual users, they don't really care about everything. They usually care more about individual things. So giving an example, why is this so? Is often if you're familiar with deep learning models, the earlier layer or the earlier feature that it decipher usually is more lower level. Lower level as in maybe detecting lines, detecting bright spot, and so on. While for the later layers would be a high level concept. So it could be like maybe about faces, about like hands, and so on. So often the understanding debugging is more helpful at the later part, right, where they can more easily interpret. The lower level part may not be as interested. Right. So to leverage that observation, so then in our Activis system, there's a screenshot of it. So we incorporate, we call the model overview graph, where we do show the whole architecture, but then we allow the user to zoom and pan and then to pick the particular modules that they're interested in, so that we don't show everything at the same time. Right? And then at the bottom, then you'll see more detail about it. So this is using the famous overview first, zoom and filter, details on demand idea. So you may say, oh wow, okay, well that's really simple. Yes, we want things to be simple. We want things to be used. Right? So and you don't need to go very fancy. So it just need to be things that work. That's important. So that's the first main idea. And the second idea is that we observe that data scientists often they analyze data using a variety of ways, different patterns. We can classify them into two primary categories, but you'll see this is actually a spectrum. So one we call instance level analysis, as in using specific examples that you pass into model to understand what's happening. So this is very similar to a writing program. It's like kind of unit testing, if you would, right? So you have particular example, you know for sure it has to be correctly classified, or if not, then something is wrong, right? So those are specific instances. So it's great for debugging, very specific. You know exactly where you're passing in, you know exactly what is wrong. Right, so that's one way, pattern analysis. But there is also the other side, we call subset level. The reason is that for instance level, it's individual example. So that means it's not very scalable. Right? So if you're talking about Facebook scale data, so you have billions of items, so you cannot really do instance level. So we need to support also subset level. Another way of thinking it is, well, so you want a group of instances analyzing at that level. And when you think about grouping instances, that means you can group it at different granularity level. You can group things by, let's say, a class. Right? You then classification, they're grouping by class, or maybe subclasses, right? There's a smaller chunk within a class, or any user-defined way. So you have a lot of data, but now you want to chop it up in different ways, right? So that we all put into subset level. In practice, we need to support both because scalability reason and also the ease of debugging. So we support both. So how do we support both? It turned out that a lot of the work, existing work, do not support that well, or at least not integrate that easily. So what we do in our Activis system, so we can focus on the lower part, right? So ignoring the top overview part, is we integrate all these kind of visualization for the different analysis in the we call a neuron activation view. Right? So where each row here, each column here would be one neuron in the deep learning model, and then for each row here would be let's say an instance or instance subset. So the data that we're looking at here is a text data. So as in like Facebook feed, you can think of as Facebook feed. For each Facebook feed, you might want to classify like what kind of feed it is. Is it talking about, let's say here, about description? Is it about abbreviation? Is it about entity and so on? So at the top rows, those are the classes, like classes of classification. So that means that that's one kind of subset, but you can also have other kind of subset, maybe more granular. So here, each dot here, the saturation means how strong the activation it is for the particular class. I'm going to step in a little bit. So you can define your own subset. For example, I only want text that contain particular words, so you can create those as well. And you can also incorporate instances into the view as well. So here on the right-hand side, we have instance selection view, where each square here is one specific instance. You mouse over it, you will see the actual text. And you click on it, then it also get added to the neuron activation view. So, right, so that means the design is actually quite simple. We use a matrix table view where columns are neurons. The rows there could be subsets, it could be class level subset, it could be user-defined subset, it could be specific instances. You can even add instances that might be misclassified. Right? So here we're using the border and the interior field color to represent what is correct and what's not. The benefit of integrating all these together is that you can now sort all the neurons based on their strength. And so allow you to easily compare. Let's say at the bottom, so those are specific instances. You know what is correctly classified, what is misclassified, and can compare the activation patterns, that means the saturation, with the classes that you should be correctly classified. And then you can see by doing the sorting, you say, wow, okay, so it's quite different. There's a lot more gaps. It's not really in the gradation going down. So that's an effective way for data scientists to spot and compare. And also doing everything in one single view. But this is what we call the unified analysis for instances and subset. And of course, for Facebook, we also need to care about scalability, right? So not going into too much detail. Use a combination of techniques. One we call guided instance sampling. So through sampling, instead of dealing with 1 billion items, we can do a sample, and then also do pre-computation. So it can be from user specify in the model which of the components that are interested in, and then we can pre-compute those activation beforehand, so that when they launch the Activis platform, they can see things in real time. And also we leverage Facebook's scalable computation backend, so that is to do a lot of the matrix computation and be able to handle the billion scale data. And now Activis is deployed in Facebook on their machine learning platform. It's called FB Learner, which is used by over 25% of engineering team. So now it's very easy for Facebook data scientists and engineers to use it. They go to the traditional view of the machine learning model. Usually once they train machine learning model, they have like a kind of summary plot, if you would, right, of all the summary statistics and so on. But then now they also have a button that they can click, and then they would launch the Activis visualization. So for Activis, it's great for understanding a single model and probably also good for some particular data set. But sometimes we want to have an even more high-level view of what's happening in the model or for a big data set. So that's some of the recent work that we have been working on, particularly one system called Summit, which is going to appear at the Visualization Conference, it's 2019, which is to aim to tackle that problem, to try to do scalable summarization and to help people understand, if you pass in, let's say, a lot of images like white wolf or the particular cats into a deep learning model, what are the influential neurons, influential connection in the neurons that all these images are really activating. So more concretely, that means we want to know what are the features or the combination of features or connection of features that the model is really discovering. Right? So what are the most important ones, what's the less important one? So that's the main idea of Summit. So there's a UI of Summit, and you can use Summit for the scenario I described, but also it's helpful for debugging, which include also understanding adversarial attack and defense, right? Because you can think of attack as a bug as in bug in your model. You are attacking it. So what's really happening? So let me show you an example of how they could be used. So in this case, we are looking at a particular class from ImageNet. So ImageNet is a popular image that is about 1 million images and it has 1,000 classes. We're looking at particularly the class called Tench. Tench is yellowfish. So we select the yellowfish on the left-hand side. And then on the right-hand side, we want to see what are the features that it has learned. Right? So remember, we want to have something kind of like a network summary. So it's fish class, but then we mouse over some of the neurons to look at the feature, look at a lot of people. Actually, people faces. And then we look higher. Oh, well, then we start to see some fish, but also see fingers. More fingers. And more people. So why is that? Right? Any guess? Actually, any guess? Why so many people? We're talking about fish. Any guess?
Only fish.
Ah, very good. So it turned out that tench is one of the kind of fish that people like to catch, and then they want to show off, take pictures. So which is why in the data set, actually most of the pictures are people carrying the fish in their hands, which is why surprising, because if you are a machine learning developer, right, data scientist, so I want a model to accurate, very accurate, but then now we found out what 99 out of 100 images for the Tench class actually are dependent on the people feature. Would you still want to use it, or would you rather maybe collect more data that's not only like a person with the fish, but maybe actual fish, most of the fish, right? So that is one example of what you can use Summit for. So we're very excited about this. This is only early work, and we want to use it through understanding both a data quality issue, a model issue, or adversarial attack. And deep learning model, as it could be like the ones on Facebook, it could be like the model like for Facebook, for Summit that try to understand. So those, I would say, are some of the earlier deep learning model. And now we also have some more recent development. And a lot of the time they are getting quite complex, right? So complex that even for experts, they might have a hard time understanding. So that, which is bring us to the second part, the middle part of the talk, where maybe our experts also need some help, or maybe our students also need some help to help with the learning of these complex model. In particular, we want to focus on a kind of model called GANG, Generative Adversarial Network. And this is work that joint work with Google, the Pair Group, based in Cambridge. And the goal there is to help with machine learning education. So you probably have seen some of these examples, maybe in classes or on the web, like TensorFlow Playground, for example, one of the very popular one on the top left there, some of the early visualization. And those are great, right? But at the same time, also they're designed more for the more classic deep learning models. And more than their deep learning model can be pretty complex, right? So it can be many layers, many components, and particular one called Generative Adversarial Network, or GANGs, was the most exciting, interesting technique. And that's even more complex. So you might already have seen a like example of this before, where you have these faces that look real, but it's actually fake, or maybe like Airbnb that doesn't exist. Yeah, so images of Airbnb, but they're actually also fake. So it turned out to be pretty complex. So why is it so complex? So if you just look at the math, that's already quite a bit of math. But we're not talking about math. So what we really want to focus on is about the core reason for complexity. A core reason is that in the GANG that generate these fake but real-looking thing is they are using two competing neural networks inside it, which create a complexity. So in particular, the two components we call generator and discriminator. So generator, you can think of it in everyday life as someone who want to make fake bills, so a counterfeiter make fake bills. And then we have the good guy, the police, who try to spot these fake bills. Of course, in the gang, this is the conceptual understanding. In practice, what's really happening is somewhat different. So what do the counterfeiter do? Counterfeiter want to make fake bills, right? So I start with some pretty low quality and try to fool the police. Then the police say, oh, okay, so it's not good. So police know the real thing, how the real thing look like. So I compare the real thing and then this is fake. But then the counterfeiter gets smarter. He says, oh, okay, I'm going to improve my thing, so I'm going to make even better bill. Right? So then the next iteration, the fake bill looks even more real. And while the police also become smarter, right? Because, well, you're getting me more realistic but fake things, I'm going to improve myself. So this is the iteration internally that's happening in gang, so that in the end, if the counterfeiter is able to produce this fake bill that is indistinguishable from the real thing, then that means you are done with training your gang. Right? So as in generating fake faces, fake Airbnb pictures. So when the police cannot tell the difference, well, that means you have a good enough generator. So conceptually, oh, okay, good, that's very nice. Well, in practice, not as easy to explain this, right? Especially with real data instead of this toy data. So how do we explain all these? So at the high level, we need to handle a couple of challenges. So the conceptual understanding, which we just described, and also we want things to be real, where people can interact with all these in real time. So interactive training, and more importantly, for education, that means it to be easy to use, right? Easily accessible by anyone. So going back to our example, so how do we achieve those goals? Right. The very first question that you might have is, what is the data to visualize? So in our scenario, we use fake bills, but in practice, when you do a visualization explanation, how do we do it? So we decided to use 2D data. 2D dimensional data instead of high dimensional. You may say, why 2D data, right? So for real data images, so those high dimensional, so why do we go for 2D? The main reason is that even for 2D is already complex enough. And also the understanding here is not so much about the dimensionality, but it's actually the interaction. So that's why we decided to use 2D and focus on the main concept, and so that we can also easily visualize the data, because once you have high dimensional data, you need to do dimensionality reduction, which means you lose information, which also means introduce another complexity in the explanation, which is why I use 2D data. So we use green dots as real, the actual real thing you want to mimic, and then the purple, which is generated data as the fake things. So iteration-wise, as in our example, right? So you want to improve your fake data so that you gradually look more real. So this is the very first version 0.1, how it looked like. So we'll incorporate and design in the final thing. So that's the generator, right? And I'm sorry, that's the data. So how do we visualize the generator iteration? So in Gang, often our starting point is actually we call random data. A random thing, you can actually fit anything to it. And the iterative improvement is, you can think of it technically as a transformation, transforming your initial random thing into something eventually look real. So another way to think about it is you are trying to map in your original data input space into something that you want. So that means you could put a grid, like a uniform grid. And what really is like kind of twisting and warping your original input space into the output space that you want, the fake but real thing. So you're kind of moving these all these area. So how do we convey this, right? So since this warping and thing will change over iteration, so that's where we bring in animation. In general, if you're taking visualization HCI class, you will know that animation, you need to use it really carefully because it can disorient people. So for this case, we think this is a really good use. So in particular, we want people to mouse over the middle part generator, and then they can play the animation on demand to see how the original regular grid get transformed, get warped. Without animation, is actually really hard to understand because you only see the output. You don't know, wait, what's the input look like? So here you can repeatedly play it and then see, oh, okay, so lower left corner, now get warped to upper end corner. So that's how we visualize generator. And what about discriminator, like the police? So that's easier. You are taking machine learning class or a little bit experience with, then well, the most common way is to use a heat map. This is what we're doing. So we use the same color coding, green for real, and then fake for purple. Right? So we visualize the decision boundary. So putting everything together, so that become our aggregate visualization. So we had real data, fake data, generator, discriminator, everything stacked together, which you can turn on and off. and that becomes the visualization. This is 0.5. So why is it 0.5? Because, well, visualization, we're doing interactive training. That means you need to somehow let the user fiddle with the parameter. So there was, okay, that's good. So we'll add some sliders. That was disastrous. That was really bad. Even bad for an expert. I should have no idea, like, wait, what are all these sliders? Oh, keep in mind that we have two competing neural networks. So actually, that's two copies of the same slider. Very, very confusing. So why is that? Right. The main reason is because the mental model is very hard to capture just by having a collection of sliders. So in the head, in people's head, is, well, you have two neural networks, they're competing, they're working together. But that's not captured using the list of sliders. So that means we really need something that do show the overview and connect everything. That brings us to our final design of GangLab, where we do show the interaction to do big rectangle here as to do two big component, and then also we show everything in between. So I'm going to show you a demo of it. So let's say we want to generate real data that looks like a ring. So then we want the fake one to turn into a ring eventually, right? So that's our goal. And we want interactive training, so that means the user can go in and then they fiddle with the parameter, learning rate, and so on of the two parameters, two neural networks, and then they can start training. They can press a play button and can see how things get moved. So fake data originally it doesn't look really good, but then iteratively it will improve. Right? The training is happening, become better. You can turn on and off the visualization. Right? Sometimes it can be pretty overwhelming, so turn on and off of them. Right, and that's just the warping, the animation that you showed, how to see the input space get transformed into the output space. And change the hyperparameter a little bit. And also you notice that we are speeding up the training at 15 times speed. So similar to common deep learning model, it takes forever. So we try to speed up. And in the end, you can, that looks pretty good. Now it becomes a ring, right? And you say, okay, can you try it at home? Yes, you can actually try it. That is our third goal, is to make it easy for people to try at home. So conventional visualization, if you want to build something like that previously, you would have a backend. Powerful backend probably costs a lot of money, Python GPU. And we think, well, that is not a good way, but not the easiest way to do it. What about we push everything into the browser? So that means everything in JavaScript. Specifically, it uses TensorFlow.js to accelerate it by WebGL. So that means for a graphics card or even modern day CPU also has a GPU component. You can do all these in your browser. So you can actually just go to Google for GangLab, and then you can go there and play with it in your browser. And once we release it, so a lot of interest, so a lot of likes and retweets. So encourage you to try it. It's safe. You can try it on your browser. It doesn't crash your browser. It may just be slow, but it doesn't crash your browser. Yes. Right. So that brings us to the last part of the talk. Right. So I have all these very exciting development on interpretable AI and also adversarial machine learning, and then there's hopefully I make the case for why we wanted to interpret AI, not just in secure AI alone, because a lot of time we don't really know what's happening. So what's the current landscape or research? Right? So we did a recent survey on this, which I encourage you to read, Visual Analytics in Deep Learning, very recent, that summarized the landscape. So in particular, the way that we do it is we take a very human-centered approach. Instead of summarizing all the points, we want to put these into the perspective of why people do these interpretable techniques, visualization, what they are really interpreting. You will see that for different use cases, different scenario, things that they're visualizing may be very different. When they may want to do it, is it to help with training, model training? Is it for helping understanding? Or let's say in GangLab, is it because they want to use it for education? Right? Who is it for? You will find that often the audience is also very diverse. It could be designed for a student, it could be designed for a data science at a company, so different skill level, right? So, and also how and why. So some key takeaway from doing the survey, I think that's a great thing for the community, is that currently a lot of the tools are still designed for experts. So we sorely need tools that are designed for, especially for students, like people who are starting only. So how do we get them excited? How do we make it easier for them to try things? You may recall that activists support what we call instance-based analysis. That means they focus on specific example, but in practice we want things to be scalable, right? So we need more work that will support that kind of scalable analysis. So And we're also we're very excited to see that a lot of the work actually going in a very good trajectory. Is very interdisciplinary, so it's no longer like happening only in one community, but now we also across communities. So we think that's a great thing. Number 4 is the actionability. So currently, a lot of tools are designed to help with more like diagnostic, as in, oh, we see something is wrong, but then they don't really tell people how to fix them. So we think the actionability is important. So also suggest what people may want to do instead of just telling, hey, something is wrong, go fix it. Right? So we want to give them people some guidance. Evaluation is still very hard. And a lot of the tools often we propose it, but then evaluation often it takes quite a bit of time to do. But we think we will have some good handle on it. The last part, yes, say of the model not very robust. I think by now you would agree with me. And that also means you want to have more techniques that help people understand all these vulnerabilities. So the remaining few minutes, I would summarize with, I would end with one of our latest work, which is from Fred Holman, who's a senior PhD student. He had a wonderful internship at MSR, Microsoft Research, and they also study a very important problem, which I try not to talk about too much, but we can escape, is what is interpretability after all? So we have been talking about interpretability AI. I try to convince you that's important, what it's really doing. So they did a study on it, and they specifically designed a tool to help understand what it is. It turned out that interpretability is kind of like data science, where there's no agreed upon definition. If you talk about people from different communities, they give you different things. So they would talk about maybe it's about the internal, discovering, understanding the operation, looking at data mapping, and all those no agreed upon definition. So for that reason, they built a tool called Gamut to help understand what do data scientists, engineers really hoping to achieve, what they really want to do when they want to interpret a model. So that means they want to study what are the capabilities of interpretability that they want to provide. And they discover a number of questions that often data scientists would like to ask, and which also means capabilities that you want tools to support, be able to support if you're working on interpretability. And more specifically, let's say we're looking at house data, look at the cost of houses, right? So what are the kind of capabilities that you wish to be able to support to help with interpretability? So it could be something about instances, but as you already saw an example in Activis, so looking at particular examples, local instance explanation. It could be about comparing things. Actually, in practice, it's very important. It's very rare that you only develop one thing. You should have multiple models, right? Multiple instance comparison, important. Number 3, now is a lot of interest on it. We call counterfactual. Very fancy name. What that really means is we're asking what if question. As in, well, not only the data that you see, but also if you change the data a little bit, what would happen? So it's very actually related to adversarial ML, because adversarial ML is you are changing the data in the ways that may not be good for the model. So that's one example of that. Finding similar thing, number 4, that's also a need. Not only looking at what you are currently focused on also finding similar thing. Right? Care a lot about error. So in practice, people do say, well, don't just give me a model. Tell me when would it break? Like what's the likelihood that it would break? Right? And also, like what Summit and Activists do, but discover what are the features that are important, what are important score. So I highly encourage you to read the paper. It was published at Kaipery recently, 2019. Very nice work. Oh, I'm going to skip this. Yeah, so you want to look at more details. So the paper, the website's up there. And for today, cover quite a bit of work. Some on secure AI side, some on the interpretable AI side, some examples on each of them. And hopefully I made you a case. So the reason I said is towards secure AI and interpretive AI because we're only starting to build a bridge. But hopefully I convinced you that the bridge is sorely needed. A lot of work on it, secure AI, also now getting more work in that, but then we should combine them and that would be great. Right. So with that, thank all the students and all the audience. Thank you. Thanks.
I think we're just about out of time, unfortunately, yes. But will you be here for a couple minutes?
Yes.
If folks have questions
yes, I will.
Afterwards?
Yep.
Okay. Thank you again,
Thank
Paulo.
you.
Great talk.
Thank you. Thank you.